Morning. So we'll get started. Before we start our new topic today, I just want to go over quickly the syllabus and see where we are. Um, Here we are today, November 7th. Okay, and I'm supposed to start module 5. Each time I repost the syllabus with the YouTube links, I also make slight adjustments to the schedule because module 3 statistics, when I was doing that, I took much longer than I originally planned, like more days than I originally planned. So everything else is getting squeezed and pushed back and so on. Anyway, so module 4, we did regressions, 2 lectures, and then we also did interpolation, 1 lecture. What I plan to do is on November 14th, I will hold the quiz for, sorry, not November 14th. Wait, we already did the quiz 4. So on November 19th, we are going to do quiz 5. Module 5 is going to be on numerical integration and numerical differentiation, which we will go over today and next Tuesday. So instead of having the quiz on the 14th, we'll have the quiz on the 19th. So that you will actually study the entire module 5 for the quiz. Okay, both topics, differentiation and integration, will be on the quiz, but the quiz will be a little later on November 19th. Okay, and as part of your homework 4, that is on module 4, there is a homework which is due November 14th. So you have 1 week for the homework and 1 week and 5 days or 12 days for the quiz 5. That's where we are today. Okay, so today and 12th, let's try to get module 5 done, which is relatively easier topic, which I'm sure we'll get through. As far as the rest of the course is concerned, I did plan to have you do a presentation on the last lecture about your homework 6, but now I got rid of that because I needed that extra day to do the review for exam 2. So no more class presentation. Homework 6 will be yet another regular homework. Okay. So I don't know if that's a relief for you. It's definitely a disappointment for me that I couldn't actually make you do the presentation. So that said, let's jump into module 5. Okay, so the two topics that we consider in this are numerical differentiation and integration. Before I always do get into the math, I want to ask you for examples of where you actually get the derivatives as well as integrals of quantities in your regular engineering practice or your research or your work. Can you give me some examples where differentiation is done, examples where integration is done?
Position, velocity, acceleration.
So for differentiation, we would write v equals ds dt and a equals dv dt, right? So if you are, suppose, doing an experiment where you drop some object, take a video of that object and you get frames. So you get the position at each time point. So you get t, t1, s1, t2, s2, and so on. So an object is like falling from some height, and you take video so that you can measure the position at each time, and you can see when the particle will reach the ground. So from the different positions, you could get velocity is change in position divided by change in time. And acceleration would be change in velocity divided by change in time. So this is an example of doing differentiation. But the differentiation you do here is slightly different from the one that you know of. What is the difference?
Like the n-1 and n-1 variable.
No, what you get here is data. This differentiation operation is done on a data set, which is t, and there is a t1 at T2, at T3, and so on. When you have a function, say if I give you s equal to 4t plus 5t squared, then if I ask you what is velocity, you would do differentiation like you learned in high school calculus, which is to write 4 plus 20t. This is doing it analytically. And this would be numerical differentiation. What we are going to learn in this module is the art of doing numerical calculation of the derivatives from a data set. Okay, so we are going to learn this, of course. Where else do you encounter integration of quantities, like something that you calculate as the integral of something else?
Areas.
Area, okay, very good. So you have a function, say f of x, of x, f of x dx from a to b, you have been told is the area under the curve. Very good starting point. Why is this area under the curve? How can you actually geometrically make the case that this actually represents area under the curve? What do you know about this dx?
Differential element of x.
It's a differential element of x. Okay, element of x. That is, you're taking any point x and you are considering another point which is very close to x. So you call this x plus dx, and this distance is dx. That's what it means, right? And when we write delta x, we mean some finite width. When we write dx, we call it differential in the limit of the delta x goes to 0. That is really small width, we call it dx. Okay. So this, let's say if I rewrite it here, I have a curve. Okay, here is let's say x, and here is let's say x plus delta x. Okay, so far just considering 2 points very close to each other, and they are separated by a finite width delta x. Okay, the value of the function at this point, okay, which we'll call f of x. The value of the function at this point will be f of x plus delta x. Okay. Between these 2 points, the function has some pattern. Okay, it could have a curvilinear pattern, something. But since this gap is so small, we could just join that with a straight line. Whatever the actual function may be, we replace or we join f of x and f of x plus delta x by a straight line. Can I do that? Because if the closer they are, the more okay it is to call it a straight line. That's what we learned in interpolation, right? When the points are really close spaced together, like closer together, a linear approximation gets that much better. So if this is a straight line and this is again like a perpendicular line, what is the area of this space? This what type of polygon is this? Where you have 2 sides parallel to each other. Trapezoid, right? This is a trapezium or a trapezoid. And what is the area of a trapezium? Of a trapezium? 1/2 times the height multiplied by sum of parallel sides. This is what you learned in your which course, maybe some freshman course or high school. Right? So the area of a trapezium is half of the height multiplied by sum of parallel sides, right? So if I take that, what is the height? So area of shaded region is half. What is the height? Height is delta x. Height is delta x. Right? That is x plus delta x minus x, that is delta x. And then sum of the parallel sides is f of x plus delta x plus f of x. Okay. So if I take this segment by calling it a trapezium, I'm able to get its area. Okay. A piece of work. Okay. So if I had a trapezium or a function f of x, which is a linear. Suppose I had a function which is a linear equation. Alright, instead of saying mx plus b, with c1x plus c2. Okay. For a linear function, f of x equal to c1x plus c2. What is integral a to b f of x dx? This whole thing is a trapezium, right? So you can write this half. What is the height of this trapezium? B minus a times f of a plus f of b. All I'm doing is just to write an obvious fact that the area of a trapezium in terms of this function. But not all functions will be linear. In general, they could be any other function, any other type of function. So what do we do? If for any arbitrary function, we would write integral a to b f of x dx is approximately equal to half b minus a times f of a plus f of b. When is this a reasonable approximation? Or how to make this a better approximation? If I consider a curve, okay, let's consider this. This is your stop writing, okay? Don't bother writing now. This is f of x. This is x. This is a. This is b. Reason with me. If I just join these 2 points. If I join these 2 points, this is f of a. This is f of b. What is my goal? My goal is always to calculate the area under the curve. My goal is to calculate area under the curve. If I just, without thinking, join these 2 points by a straight line and get the area of the trapezium. So what is the area of the trapezium? That is b minus a, or half of b minus a times f of a plus f of b is the area of the trapezium equal to area under the curve, or is this equal to a to b f of x dx? You tell me. Is the is the area of the trapezium equal to the area under the curve? Clearly no. The more funky or non-linear this curve is, the worse this approximation becomes. Right? But if here is your A, okay? Instead of considering the entire width, suppose you take a segment here. Suppose you take any point here and an adjacent point here. Calling this a trapezium isn't that much of a stretch. Would you agree? You take a tiny segment of that interval and drawing two parallel lines. So I'm going to take this point and take an adjacent point and say that this portion can be called a trapezium. If I'm interested in area under this portion of the graph and I call this a trapezium, is that a reasonable approximation? The smaller that width is, it gets better in approximation, right? So my goal still remains the same. It is to compute the integral a to b f of x dx. But instead of doing it for the entire interval, I'm going to segment this into subsections and compute the area of each subsection and add all those up. Would that be a better deal? Why it would be a better deal? If I take subsections that are really much smaller than the width of the entire interval, get the area of each of them using the trapezium formula, and then add each area. So suppose this is A1, this is A2, this is A3, this is say AN, and the total area A to B f of x dx, I'll say is equal to A1 plus A2 plus and so on AN. Is this a better way of doing this than just calling the entire area of the trapezium equal to the width of the interval times the sum of the parallel sides? So the more finer you make the intervals, the better this approximation becomes. Why? Why would it become a better approximation the more finer you chop up these intervals?
Difference between the points for each area would be small.
The finer you chop them, calling them a trapezium gets to be a better approximation. It's more reasonable to call something like this to be a trapezium than something like this to be a trapezium. Okay, so this approximation gets better for larger values of n. So if you take this interval, if you divided this into two segments versus 5 segments versus 100 segments, guess which number of segments will lead you to the most accurate answer? 2, 5 and 100. Obviously 100 will get you a better answer, right? And we are going to see that quantitatively now. Let's do an example and see how this whole thing will work out. Okay. So I want to do I'm going to do integral 0 to 1 e power minus x dx. You know the answer going in. Okay, we'll say I equal to this, and we'll also say I exact equal to 1 minus 1 over e. You know the answer. Can somebody tell me this? 1 minus 1 over e.
Zero point six three two.
0.632. One more decimal point.
1.
Okay. 0.6321. That is our bullseye. That is the target, the exact value of this integral. Now we are going to solve this. Imagine this function. Plot this function x. Here is 0. Here is 1. The function starts at 1 and drops down and goes up to 0.63. Sorry. What is e power minus 1? 0.37. This is basically e power minus 1. What I'm asking you is for this area. We are asking you for this area. Let's do n equals 2 segments. And these segments will split them in equal proportion. So we'll have x values starting at 0, 0.5 and 1.0. That is, I'm going to write, this is the function. I'm going to have 0.5 here, and this is 1. I'm going to join 0 and 0.5 by a straight line, and 0.5 and 1 by a straight line, and I'm going to get the area of this curve, sorry, this trapezium, and the area of this trapezium. So we'll call this A1, this as A2. We are going to get A1 plus A2 and see if it agrees with I exact. So f of 0 is 1, f of 0.5 is e power minus 0.5, and this is e power minus 1. Can you tell me what is A1 and A2 by your knowledge of geometry? A1 is half 0.5 minus 0 times f of 0 plus f of 0.5. So this is half of 0.5 times 1 plus e power minus 0.5. I need a volunteer to compute and tell me this number.
Point 4016.
1 point.
0.4016.
Okay, thank you. 0.4016. Okay. Can you also compute A2? A2 will be, A2 is this segment, half of 1 minus 0.5 times f of 0.5 plus f of 1. So this is again half of 0.5 times e power minus 0.5 plus e power minus 1.
Like 2, 4, 3, 6.
Thank you. 0.2436. So if we check what is A1 plus A2, that comes out to be 12, carry over 1, 4 plus 1, 5, 4 plus 0, 4, 2 plus 4, 6, 0.6452. So A1 plus A2. So for n equals to I exact, right, 1 minus in divided by I exact as a percentage. So for n equals to in is 0.6452. So this will be 1 minus 0.6452 divided by 0.6321. Can you tell me as a percentage? Minus I'm just tabulating the calculations we are doing. For two segments, the IN value is 0.6452. And the error is exact or 1 minus the computed divided by the exact value. Minus 2%. Thank you. Minus 2%. Okay. So then let's do 5 segments. So I'm going to quickly switch over to an Excel sheet. Okay. So if we do 5 segments, or maybe we'll do 3 segments. How will you divide up the segments? What are the points you are going to get if you divide 0 to 1 into 3 segments? 0, 1, point, or 1 by 1/3 and 2/3. So this is segment 1 or A1, A2, A3. Yeah.
Why write it as a negative 2% error?
Because and it's just a way of looking at it. I always benchmark my calculation against the exact value. So it is exact minus the calculation. That's why it has a negative sign. It deviates by 2%, but in a specific direction. That's what this negative shows. Okay. You can do it the other way, nothing wrong. Yeah, as far as when you say it, you should say 2% below or above. That's so if I'm dividing this into 3 segments, where I'm going to draw my curve, this is f of 0, 1, this is e power or f of 1 by 3, f of 2 by 3, and then I have f of 1. So I'm going to just draw trapezia. And I want to get the area of these three polygons or trapezia to get I. So if I say I, n equals 3 is A1 plus A2 plus A3. This will be half, 1/3. 1/3 is the width of each interval. Half of 1/3 multiplied by f of 0 plus f of 1/3. That is for the first segment. And then f of 1/3 plus f of 2/3, that is for the second segment. And then plus f of 2/3 plus f of 1, that is for the third segment. Don't yet jump into calculating. What I want you to see is this is half of 1/3 times f of 0 plus 2 times f of 1/3 plus f of 2/3 plus f of 1. Okay. Again, don't start computing. Look up. Look up, don't write, take a break. So when we have 3 segments, for n equals 3 segments, we get In equal to half 1/3 f of 0 plus 2 times f of 1/3 plus f of 2/3 plus f of 1. All right. What is this 1/3? That is the width of each segment. That's the width of each segment. To deconstruct that 1/3, one happens to be 1 minus 0, or it's the width of the interval in which you are doing the integration divided by what is 3? 3 is the number of segments. If I give a symbol, integral a to b f of x dx, this 1 is nothing but b and 0 is nothing but a. Okay, so I can write 1/3 is nothing but b minus a divided by n, where b is 1, a is 0, n is 3. With me, Parker? Okay. Okay. All right. What is this f of 0? F of 0, you can write this as f of a. That is the function evaluated function at the start of the interval. Function at the starting point of the interval. Same thing with f of 1. F of 1 you can write this is f of b at the end point. I'll let you catch up on writing. You're right. Done. So we have generalized f of 0 and f of 1 and 1/3. What about these points? F of 1/3. So 1/3 you can write is 0 plus 1 by 3. Or in other words, this is a plus b minus a divided by n. And I'm going to give this b minus a divided by n multiplied by 1. So I'm going to give this a symbol. I'll call this delta or delta x. Okay, delta x, and this is I equal to 1. So I'll write x1, which is 1/3, is A plus delta X times I. I can also write X2 is 2/3 is A plus delta X times 2. Or in general, Xi is A plus delta X times I. What I'm basically telling you is, just like you did 3 segments, you could do 5 segments, 10 segments, 100 segments, n can be any integer. Okay, so this middle part here, function evaluated at all points between A and B. So if I put all this together, In equal to delta X divided by 2 times f of A plus f of plus 2 times summation I equal to 1 to n minus 1 f of xi plus f of b. What is delta? Delta x happens to be b minus a divided by n, width of the interval divided by number of segments. When n becomes a large number, you don't want to do this manually. You want to use your MATLAB or Excel or something, right? So this formula is the trapezoid rule, trapezoidal rule. It's given as equation 21.10 in the text. Some question? So, according to this nomenclature, here is the x-axis, here is A, here is B, let's say. In the middle here, we divide it into x1, x2, x3, up to xn minus 1. So by this logic, the first point should be x0 and the last point should be xn. Okay, so the book, instead of using A and B here, they put x naught and they put xn here. Where x naught is A starting point, xn is B ending point. Okay, and instead of using delta x for some weird reason, they are using b minus a divided by 2. It's the same thing. So this sorry, b minus a, yeah. Oh, 2n. B minus a divided by 2. Thank you. So this is delta x. Delta x, which is b minus a divided by n. So
Why is that 1/2 and 1/3 at the top?
yeah.
Yeah, that one's.
So this 1/3 itself is width of the interval. So this delta x here is 1/3. Because the 1 is nothing but 1 minus 0 and 3 is how many segments are you dividing it in? That's why it's 1/3. So I'm taking a length of 1 and
Yeah.
dividing it into 3 segments. That's what this is. You're okay? Okay. All right. So this is one of the simplest integration formulas. And we took a problem in which we knew the answer going in so that we can estimate the error as you do more formulas or more number of segments. So if you do the same thing for 3 segments, you can evaluate and the error will be something. And the error will go down. Error reduces as n increases. Okay. When you do a integration of some function which you don't have the exact answer, like for example, I'm asking you to evaluate something like 0 to infinity e power minus t squared dt. Let's suppose you don't know or to make it a little more complicated, like t power 4. This one has no analytic formula. We don't know the answer. But I'm asking you for the value of the integral. How would you approach this situation? How will you select how many segments to use in order to get a result that is reasonable and accurate? First of all, look at the integral. It has 0 to infinity. Are you going to take a interval which is infinite in length and start dividing it into segments? What are you going to do?
Small portion.
You might also want to note this along with the observer. Okay, what were you saying?
Like the smaller portion.
Select a smaller portion. How do you select which portion is the one to select? So this function here, e power minus t power 4 is the one you are integrating. Okay. And you are integrating this over from t equal to 0 all the way to infinity. First thing you would do, step 1, is to plot the function. So that you would have an idea how quickly it decays and becomes 0. So even though this is 0 to infinity, 0 to infinity of e power minus t power 4 dt is practically 0 to some value a of e power minus t power 4 or 0 to b dt. This happens to be b. Because after b it's practically 0. Narrow the range into something finite. Okay. Then step 2, choose a guess value of n. You don't know whether it's to be perfect, but choose some value, let's say 10. Get an answer for in. Okay, get in. And step 3 will be to assess your choice. Suppose you doubled n. Step 3, assess by, let's say, doubling n. When you double your n, for example, and your in changes a lot, what does that mean? It's getting more accurate. So if it is on the way to getting more accurate, you double the n. That is, you did initially 10, n equals 10, and then you did 20. The value of I changed a lot, which means you are still evolving. So you should try one more time to double n. Double is just a suggestion. You could do 5 times more, or you could do 1.5 times more, that's okay. You should again increase n and see if I changes again. As you do more n values or higher n values, if your I stops changing, which means you can stop, right? There is no more gain in accuracy for increasing the number of segments or increasing the amount of work you need to do. Okay, so this is how practically you think about integrating functions for whom you don't know the answer. And that's most often where you use the integration, because if you can integrate it directly, you wouldn't use numerical integration. Okay, shall we do a problem with Excel? Yeah.
So on the test, are you gonna ask us to get the values for given n's? Because why wouldn't I just take like n to 1,000 the first time and then?
In a test, usually the only thing you have is a calculator. So I'll basically tell you what n to use.
Yeah.
So that I can test whether or not you understood the most basic aspect. If I give you an Excel sheet and tell you do what you need to get me the most accurate answer, then you would do all this. Okay. So this sort of integration problem is definitely something you can expect. There are few more methods that we will learn. So this one here, I'll keep this up just like this. This is called trapezoidal proof. Okay. There is one more method that we want to learn. Simpson's 1/3 rule. Simpson's 1/3 rule. Okay. All right. So when we discussed just now about a curve that looks like this, and you have A and you have B. What is the core of trapezoidal rule? When you take a segment, and you connect these 2 points, turn this into a trapezium, what exactly you are approximating the function to be? You are saying you are ignoring whatever the original function is and replacing it with a straight line, right? So I'll write trapezoidal rule approximates f of x as a straight line, as a linear function between 2 points of a segment. This is the core. If you can call it a linear, you can also call it something else, can you? Linear is one way of fitting a function. Can you think of one other way, one more way? You can call it quadratic. Like you can approximate it as quadratic, can you? But what is the catch with doing a quadratic approximation? 2 points define a straight line. How many points do you need to define a parabola? 3, right? So you can't just do this with 2 points. You need to involve a third point. We'll call this A. I'll call this B and C. So if I have 3 points, I'm going to redraw this. Okay. Redraw this. So here is my function. I have point 1. I'll call it x0, x1, x2. Right. X0, x1, x2. Forget this original function. Okay. If I have 3 points, I can draw a parabola that passes through 3 points. Can I? Can't I? If I have 3 points, I can define a parabola. One of the point is x naught, corresponding value of the function is f of x naught, x1, f of x1, x2, f of x2. Once I say this is the parabola, I can integrate this function. That is, I can integrate the area under the parabola. The real question is whether or not that parabola realistically approximates your original function. And how will you ensure that? By making this segment as small as possible, by choosing as many segments as possible. Okay. So Simpson's 1/3 rule approximates f of x as a quadratic function between, or I should say quadratic function passing through 3 consecutive points that form a segment. Previously, we said 2 points form a segment. Here, our segment has 3 points, and within that 3 points, there is a midpoint as well. Have a question? Okay, take a pause. Listen. Look at this segment. Between x0 and x2, there is a quadratic function. If I tell you 3 points and ask you to fit a quadratic function, you can do that by what we learned in the last module, although it was relatively recent. We can use either Newton's divided difference formula or Lagrange's formula to fit a parabolic function. And we are not going to ask you to fit it. We are going to write it and then cut to the final result. Okay. So you see figure 21.10. You could have 3 points. Suppose one point is here, 1 point is here, and 1 point is here. The true function could do something like this. You don't know. You just know 3 points that are consecutive. And using the 3 points, you are fitting a parabola that runs through the 3 points. Okay. And this function here, we'll call it f of x. That is the function you care about, you want to integrate. This function here, we'll call it f2 of x. This is the quadratic approximation. Okay. What you are seeking is I equal to a to b f of x dx, where x naught equal to a, x2 equal to b. We'll say this is approximately equal to integral a to b of f2 of x. What am I implying by saying this? When I say what I seek is this, but I'm going to say this is sort of this. Because although the true function may be something which we may never know, we are using quadratic approximation to say the function it could be a quadratic, and if it is a quadratic, the error is basically the area that I shade here. Whatever I do, I'm going to get an error associated. If I make my interval smaller, suppose my interval is only here, and if I have one more point in here, my quadratic will be a better approximation of the original function. The smaller your segment is, the better things get, more accurate it gets. Okay, so we can write an expression for f2. We can write an expression for f2, which is using Lagrange polynomial, second order Lagrange polynomial, and that would be x minus x1. Not that we are going to actually do integration on this, but I'll just write it. This is f2 of x, Lagrange second order polynomial formula. Second order Lagrange polynomial. Polynomial fitted to 3 points x0 comma f of x0, x1 comma f of x1, and x2 comma f of x2. With me so far? No, yes. Yeah,
So for like this is if we don't know the function.
yes. No, this is like saying you will be given an integration. Suppose this is e power minus x cube or something, some complicated function. It's almost like saying, although this function is complicated, I'm going to take a tiny segment over which I'll call this function or approximate this function to be a quadratic. That's what this means. Your real function is whatever it is, but so it's like saying if my function is e power x, if I consider from 0 to 0.1, 1 plus x is actually a very good approximation for e power x in that tiny interval. But if my interval is up to 10, 0 to 10, e power 10 is a humongous number. So you can't call it linear. You can't approximate it with 1 plus x. 1 plus x at 10 is what? 11. E power 10 is some large number. So it's isolating your function to a small portion in which it is almost looking like a linear. In fact, if you want some history, when people first started looking around and they realized that you look up the sky, there are celestial objects, and the ground is flat. That's how they thought the earth must be flat. Because in their perception, for whatever range that you can see, you can't see the earth's curvature unless you go high in altitude where you can start seeing the earth curving around you. Okay, so that's how you get to think that, okay, then you can say that this room is flat, maybe this campus is flat, but if you go higher in altitude, you can't say the whole region of Memphis is flat because it's big enough to start having a curves. So this is a quadratic function. Everybody agrees with me? It is x minus, it's a second order polynomial. If we can do integration on polynomials, we know that, right? You know that x power n dx is x power n plus 1 by n plus 1. You know that, don't you? So if I say this integral is approximated with integral a to b of f2 of x, and I plug in f2 as this, that can be done. We are not going to do it, but we are just going to write the final result. We are going to write I approximated as a to b f2 of x dx is nothing but b minus a multiplied by f of x naught plus 4 times f of x1 plus f of x2 divided by 6. That is our segment here. That is, we take the entire segment, okay, and we divide it into 3 points: x0, x1, and x2. So this is the width of the segment, and b minus a divided by 2 is the, I'm sorry, b minus a divided by 2 or 3, 2. No, let's just leave it at that. I don't want to clarify. So this result here is I Simpson's 1/3 rule, b minus a divided by 6 multiplied by f of x naught plus 4 times f of x1 plus f of x2. The reason I rewrite this is I always use a memory trick to remember these things, which is this is big. This number is just have something you have to memorize or remember. Okay. This is function at the starting point. This is the function at ending point. This is nothing but 4 times the function at the intermediate point.
Why is it 4?
If you do the integration, it's basically the number will pop out. That is, if you plug in this function into here and carry out the steps, that 4 and 6 will pop out. Okay. I need to take a very short break to the restroom. I'll be back just 1 second.
Yes, that's going to be a new function, right? It's a straight quadratic function. You're still converting it into like straight second decimal. These are like the complex functions.
Sorry about that. So, I mean, like I was saying, if you plug in this F2, you would go through the integration and arrive at this formula. This is for one segment. Within a segment defined by 3 points, you get this A or this value. Okay. You have a question? No? Good. So when you are doing a practical problem, you're just not going to do it exactly one segment, because one segment will lead you to the most inaccurate answer you could have. You want to do it with a larger number of segments. Okay. So let's do an example. Okay. Same problem as before. We want to do I equal to integral 0 to 1 e power minus x dx. Okay. This time with Simpson's rule, Simpson's 1/3 rule, and we'll do it with n equals 3 segments. Yeah.
Oh, try to get a better approximation.
Yes, there is trapezoidal rule is like a lower order approximation. Simpson's rule is one level higher. It calls the function as quadratic instead
But
of.
both of them could be used for any function.
You can use any method for any function. The question then comes to which is more accurate for the same computational expense, or for or which will get you to the most accurate answer with least number of operations. So you look at this and say you have this, and you are going to have one more formula, in equal to b minus a divided by 3n times f of x naught plus 4 times I equal to 1 to n minus 1 plus f of xn. This is Simpson's 1/3 rule. You will then have to figure out which will get you more accuracy. Which we are going to do. We'll do a comparison of the two methods for the same problem. Okay. So you are going to do okay, I think I made a small mistake. Up to here is correct. Okay, this formula, the way I've written this as a small mistake. So let me step back. All right, do you have a question?
Yeah, I was just, I guess I was, they're both using like, I guess the differences between it.
I'll tell the difference. So when you think about segments for the trapezoidal rule, your segments are trapezia. Okay, defined by 2 points. So if you have x0 and x1, they define one segment. So this is a segment. And then between x1 and x2, you have a second segment, another segment. Okay, so if you take your interval a to b and you say you are dividing this into n segments, how many points are going to be there? x0, x1, x2 up to xn minus 1, and b is nothing but xn. So each of this is a trapezium. That is the segment. When it comes to the Simpson's 1/3 rule, let me redraw this. You have your x0 and you have your xn. Okay, and you divide this into the same number of points, x1, x2, xn minus 1, xn minus 2, and so on. Okay? 3 points together define a segment here. You need 3 points to define a parabola, right? So these 3 points, they fit a parabola or they define that parabola. So each segment consists of 3 points. Here each segment consists of 2 points. You will still say I will have n segments, but each segment is defined by 3 points. Here each segment defined by 2 points. So we are already placing a constraint here. Over here, if you have a width, you can do any number of segments. You can do odd number or even number of segments. Here, you can do only one type of segment. You can only do 2, 4. That is, I'm dividing this into 2 intervals. So basically, I'm adding one more point. If I add, say, suppose I did x1 and x2, I'm in trouble. Because if x0, x1, x2 define one segment, the second segment is not defined. Right? So I'll have to do x0, x1, x2, x3, and x4. So that these 3 will define a segment and these 3 will define the next segment. Is that making sense to you? So we are adding 3 points between the 2. We added 1 is okay, 3 is okay, 5 will be okay, but 2, 4, 6 will not be okay. What? Did you say what? So when I have trapezia, if I have 2 points, they define that trapezium. Okay, so suppose I take the interval A to B, or I'll say x0 to xn. If I added one more point that defines 2 segments, this is segment 1, this is segment 2. With me so far? You need to give some reaction, like you did when you didn't understand.
Well, you said, what confused me was you said 1, 3, and 5 together, 2, 4, and 6 is not.
For the number of points, if I add 3 points between the extremities, it is okay. If I add 5 points, it will be okay. But if I add 2 or 4 or 6 or even number of points, it will not be okay. I'll tell you how. I'll repeat what I said. Okay. So you're good with the trapezium thing? If you add x1 and x2 and x3, you have 3 segments. You're good with this? Okay. So now we move from trapezium, which is like a straight line, to a parabola. You need 3 points to define a parabola, correct? So if I started with A and B, so this is x0. If I add 1 point between A and B, let's say this is x1 and this is x2. These 3 together define a parabola. So all this 3 is just one segment. With me? If I did x1, x2, x3, and x4. 0, 1, and 2 together they define a segment. 2, 3, and 4 together they define a segment. So this has 2 segments through 5 points or 3 in between. You got it now? So then if I did, suppose instead of doing like this, I did x1, x2, x3, x4, x5, and then x6. 0, 1, 2 will define a segment. 2, 3, 4 can define a segment. But for the last segment, I am one short. I cannot be calling that a segment. So this is not allowed under Simpson's one. This type of division is not allowed. Okay, so all right. It's geometrically very intuitive, but the math can be a little unsettling. So that's why I'm going a little repetitive. All right. So we are up to here, right? So now when we write in, I'm skipping some steps here. I write b minus a divided by n. Okay, this is what is b minus a divided by n? That is the width of any portion. That is, yeah, that is the width of any portion. So I have x naught equal to a. I have x n plus 1, or sorry, x n equal to b, x1, x2, and so on, xn minus 1. This width is b minus a divided by n. Would you agree with me? Okay. The only thing you have to remember is 3 defines a segment, or 3 together define one integration interval, and so on. Yeah.
So if you had 0, 1, 2 for one segment, and then could you reuse 2 for 2, 3, 4?
Yeah, you can do that. You can use the endpoint. Endpoint can be common.
And 4, 5, 6, and then 3, 6.
Yeah, so 0, 1, 2 form one segment, 2, 3, 4 form one segment, 4, 5, 6 form one. The midpoint cannot be shared. Endpoint can be shared. Okay, so we have b minus a divided by n multiplied by f of x naught, which is the first point. Okay, plus 4 times 4 times summation f of xi, where I takes values that are odd, 1, 3, 5, and so on, up to n minus 1, plus 2 times j equal to 2, 4, 6, only even numbers up to n minus 2, and f of xj plus f of xn. Okay, so what is the constraint on n here? Can you choose n on any any even value or any odd value? So this is the formula for the 1/3 rule. Okay. What if n is odd? What happens? Is it forbidden or is it okay?
No.
N odd is not okay. What happens when n is even? So I have, you can do this by simple example. My little brain sometimes can't look at the symbols and figure it out. So I take one example and do it. So I have x naught, x, okay, paired 1 point, x1, this becomes x2. This is okay. If I add x naught, x1, x2, x3, this is not okay. Right, because this segment is okay, but this segment is one shot. So if I do x naught, x1, x2, x3, x4, x5. Wait, up to x4. So no, up to x5, sorry, x5. So then this is okay, but wait, this is also not. Yeah, this is okay. So when I do 3 points in between or 1 point in between, it's okay. So then what is the conclusion? N can go up to x1 or it can go up to x3. So this n value, n has to be even. It can either be x2 or x4 or x6 and so on. So only constraint is n has to be an even number, which you have to remember in your notes or mind or something. And I think there is one more thing I need to divide by 3. 3n. 3n. So the common mistake students would make is when they are doing a problem like this one, for Simpson's, sorry, for trapezoidal rule, you can do 3 segments. It's okay. But for Simpson's rule, you can only do 2 or 4. Right? You can only do either 2 segments, 1, 2, or 1, 2, 3, 4. 4 intervals. Okay? So we are, how much time we have? 4 minutes. That's a lot of time. So are we good with this? Can I erase it for 1 second? So I'm going to ask you, compute 0 to 1 e power minus x dx using Simpson's 1/3 rule and n equals 4. We'll just write that, at least we'll see how far we can get. So that way we'll have I is equal to b minus a divided by 3n. What is b minus a divided by n? That is 1 minus 0 divided by 4 or 0.25. So you have 0.25 divided by 3 multiplied by f of x naught. Okay, I should tabulate what is x naught, what is x1, x2, x3, x4. X naught is a is 0, x4 is b is 1. This is what you do in your test. Make a little table with x and then f of x. You should also remember, or I mean, you should understand xi is nothing but x naught plus I times delta x. Where I runs from 1 to up to n minus 1. X1 will be 0.25, x2 will be 0.5, x3 will be 0.75. So this is e power minus 0.25, e power minus 0.5, e power minus 0.75, and e power minus. Last thing for today. Okay. So I with n equal to 4 is, what is b minus a divided by n? that is 0.25, 0.25 divided by 3 multiplied by f of x naught, which is 1 plus 2 times the odd values. 2 times the odd values, which is this and this, e power minus 0.25 plus e power minus 0.75 plus 4 times the even numbers. That would be this. Four times e power minus 0.5 plus the end value, which is e power minus 1. This is how I did this when I was doing this for the first time, which is to say this is the start or 0, this is the end or n, and then you can split everything as odd and even. Okay, so the way you would remember this formula is in equal to width of width divided by 3 times function at the start plus 2 times sum of odds plus 4 times sum of evens plus function at the end point. This is how I remember it. Okay, so please complete this, get the number and compare n equal to 4 using trapezoidal rule versus n equal to 4 with the Simpson's 1/3 rule versus exact. This sort of question is very much expected for your quiz, okay? All right, thank you, and we'll meet on Tuesday again. Okay, thank you. So next week is not your quiz. I just want to make sure that is clear. Your quiz is not next week. Quiz on this topic will be not next Tuesday, but the following Tuesday.